Well, thank you very much for the invitation, and I'm very sorry for not being able to be there in person and for technical difficulties yesterday, so hopefully this one will work. I'd like to tell you a little bit about my group's work on quantum dots in optical nanocavities and coherent control of quantum dots in optical nanocavities. So we can move to the next slide. Now click. Okay, I'll first describe you very briefly the main ingredients of what we do. Next slide, click. First, quantum dots. In our experiments, we use indium arsenide self-assembled quantum dots grown on gallium arsenide by molecular beam epitaxy. You can see on top left how they look like in the cross-section, and also on the bottom left you see AFM image of 1 micron square array of these quantum dots. They have discrete transitions between 920 and 940 nanometers, typically. But also in the bottom left, you see that there is a discrepancy in the sizes and shapes of these quantum dots, which leads to variation in quantum boxes that confine carriers, and that leads to discrepancy in transitions or inhomogeneous broadening. So we have these artificial atoms, quantum emitters that have narrow spectral lines in this range, but also all quantum dots are different from each other, so we have to worry about tuning them onto resonances and onto each other. These quantum dots that you see in the experiments that I'll describe today were grown either at Stanford by my postdoc Tomas Sarmiento, or for the older experiments by Pierre Petrov, now emeritus at UCSB, and also Seth Bank at UT Austin. Click. So this is another important ingredient of our work, photonic crystal cavity. I guess you heard a little bit yesterday from Misha, at least in his talk, on one-dimensional nanobeam cavities, which are very similar to these ones. These cavities confine light by distributed Bragg reflection laterally, so we drill arrays of air holes inside of gallium arsenide slabs surrounding quantum dots, and vertically they confine light by total internal reflection. And quantum dot is somewhere in this central region, as you see, where it's very well coupled to the optical field, and pattern of the electrical field is shown on top right. Click. So these cavities have very good quality factors. In our experiments, typically we work with cavities that have quality factors greater than 10,000. They can go as high as 25,000 for this wavelength range. And optical mode volumes are very small. They're smaller than cubic optical wavelength, and these good quality factor and small mode volume lead to very strong interaction, even strong coupling regime of cavity QED between quantum dot and the field. Click. Okay, so when we embed quantum dot inside of the cavity, in the structure such as the one shown on the right, we basically build a solid-state platform for cavity QED, which is in many ways equivalent to the atomic physics platform for cavity QED shown on the left that people have been studying for many years, for decades. But the advantages of solid-state platform are that first it has microscopic scale. Everything is on-chip integrated. We don't really need to trap atom, but we don't need complex trapping apparatus because quantum dot is naturally trapped inside of the resonator. And maybe one of the most interesting properties is that it has very high speed, as you see from later experiments. Coupling strengths are in the tens of gigahertz range, so this setup, this solid-state system has tens of gigahertz speed. But the disadvantages relative to atomic physics platform are that first, not all of the emitters are the same. Quantum dots suffer from inhomogeneous broadening. And also this system has to operate at cryogenic temperatures because these particular quantum dots at room temperatures lose confinement, and carriers can be thermally excited into surrounding semiconductor gallium arsenide. So we have to cool them down. Click. Okay, so speaking of solid-state cavity QED experiments, here is, for instance, an experiment showing the strong coupling regime between a single quantum dot and a photonic crystal cavity shown on the left. In this case, we have a coupling strength G, which exceeds loss rates of the system, cavity field decay rate, and dipole decay rate, or line width of the quantum dot. And typical experimental parameters are shown in the bottom right. So we have G, which is 10 to 25 gigahertz, dipole line width, or dipole decay of the order of a gigahertz or so, and cavity field decay rate of 8 to 16 gigahertz. And on the top right, you see what happens when we tune quantum dot onto the cavity resonance. Cavity resonance splits into two peaks. This is a well-known Rabi splitting, and from the splitting, we can infer G. Click. On the left, you see how we perform these experiments. We use temperature to tune quantum dot across the cavity resonance. We can also do it electrically, but in this particular case, it's done via temperature. As we increase temperature, we increase quantum dot wavelength. So temperature increases downwards on this plot, and then wavelength of quantum dot, which is a narrow line, increases much faster than the wavelength of the cavity, which is a broader line. And this is because the energy gaps of indium arsenide and gallium arsenide are more temperature sensitive than refractive index, which determines cavity resonance. And in this particular case, you see very well-known anti-crossing in the region where these two curves cross. And from the cross-section of this horizontal cross-section, you obtain Rabi splitting shown on the right for another system. Click. So this Rabi splitting, as same as in atomic physics, is visible in only if we probe transmission through the system with a very weak probe. In the bottom left, you see what happens as we increase the probe power, intensity of the laser beam that we transmit through the system. And this is a very well-known saturation behavior when the probe intensity becomes comparable to a photon per cavity photon lifetime. Roughly, then the system saturates and the dip in Rabi splitting is lost. So we go back to an empty cavity transmission. This particular behavior can also be employed to do all optical switching with very low power at the level of a photon or few photons and with very high speed. And that's shown in the experiment on this slide. And the cartoon on the right explains what we do in the experiment. We have a strongly coupled system consisting of a quantum dot in the cavity, and we send a laser pulse, which is very weak. It has the bandwidth that fits within the dip of the strongly coupled system, but it also has insufficient power to saturate the system. And since the frequency of this pulse is at the dip in the transmission spectrum, the pulse would bounce back. However, if it's escorted with another pulse, and that's shown in the bottom picture of the cartoon, these are resonant pulses, but they have together jointly enough power to saturate the system. As shown in the figure on the bottom left, the system saturates, transmission rises, and we expect these two pulses to propagate together to the other side. So as a result of the saturation behavior, we can switch the transmission to the system with a very weak optical pulse, and we basically can demonstrate AND gate or optical switching with very low powers. So in this experiment, we exactly did that with two pulses, and we measured transmission through the system as a function of time delay between two weak pulses. And the result is shown in the middle, subplot D. Here we plot transmission through the system as a function of time delay between the two pulses. And as expected from the cartoon and story that I just told you, when the delay becomes comparable to the pulse duration, then transmission rises, and again, if delay becomes large, then pulses miss each other at the cavity. The situation corresponds to the top picture in the cartoon, and transmission goes down, right? So that theory also predicts that. That's shown on the top, and the setup is shown on the top left. Practically with this system, we can do very low power optical switching. Here we used 40 picosecond pulses, which leads to 25 gigahertz speed, and the bandwidth or the speed of the switching process is determined by the dip in the transmission, basically 2G of the strongly coupled system, which for us is on the order of tens of gigahertz. And that's one of the reasons why I said that solid-state cavity QED systems may be mostly interesting, in addition to some solving some experimental challenges relative to atomic physics systems that are also very interesting because of their very high speed. Click. Okay, another thing that we expect to see in a strongly coupled system is formation of the ladder of dress states. Energy eigenstates of the strongly coupled system are described with this anharmonic ladder, and the new eigenstates are entangled states of the quantum dot in the cavity field, as opposed to an empty cavity which has eigenstates that are given by the Fock state, and that's shown on the left part of this curve, which form a harmonic ladder. The separation between new energy eigenstates is not constant. And this can be used to demonstrate effects of photon blockade and photon-induced tunneling that will be described on this slide. So click. So if we imagine that we send a laser beam with a frequency given by the blue arrow, then this laser can place one quantum of excitation, one photon, into the first eigenstate. And these eigenstates in the first manifold are formed by combining one photon with the quantum dot states. So basically, we can place one quantum of excitation there, click, but all the other photons from the input laser pulse cannot be placed into the system because of the unharmonicity of the ladder. There are no eigenstates corresponding to energy of that photon in the higher manifolds. Because of that, the effect shown on the top right in the cartoon, called photon blockade, can be demonstrated. So from each laser pulse in this frequency, once we couple the first photon, the presence of that photon in the system blocks all the other photons from coming in. And it's a direct result of the unharmonicity of the ladder. And some people also refer to this effect as fermionization of photons, because presence of photon blocks all the other photons from coming in, although they're bosons. This effect was first demonstrated in atomic physics in 2005 by Jeff Kimball's group, and we did it in solid state in 2008, and it was followed by us in improved form later and by other groups, including Imamoglu's in 2012. Click. Other interesting effects can happen for lasers with different input frequencies. For instance, with at the frequency given by the red arrow, we reach second manifold via two-photon process, and we can exactly place two quanta of excitation in the second manifold because these states originate from hybridization of two-photon Fock state and the quantum dot states. Click. This means that in this particular case, we would be filtering photon pairs from the input laser. And of course, input laser has Poissonian statistics. So we would be coupling in photon pairs and transmitting photon pairs to the output. And we refer to this effect as photon-induced tunneling. And of course, we can filter also 3 photons if we reach the third manifold and so on. Click. So the idea here is that we can probe unharmonicity of the ladder by looking at the transmission of the laser beam. But also, we can use this effect to filter out specific photon states and to generate n-photon Fock state by tuning the laser frequency. Click. Click. Okay. Okay, so to probe these effects, we measured statistics of transmitted photons as a function of the laser frequency. We use strongly coupled system, and we measure statistics of the transmitted photons. So at the input, we have a laser that has a Poissonian statistics, but at the output, we should be primarily filtering specific Fock state, according to the story that I just told you. So click a few times. More, yeah? And one more. Okay, so here is, for instance, what happens in the photon blockade. We measure G2 using this Hembury-Brown twist type setup. And of course, for just a laser, we expect to see all the peaks in this G2 measurement to have the same height. But in our case, the central peak has a suppressed height relative to the side peaks. And that's sub-Poissonian statistics that originates in this regime of photon blockade. Then click a few times again. If we perform the same experiment, but just change the frequency of the input laser to the one given by the red arrow, we have the regime of photon-induced tunneling, and there we observe super Poissonian statistics. And click again. And if we map G2 of 0, so just the normalized amplitude of the central peak, as a function of the detuning of the laser from the empty cavity, you can see that in some regions, G2 of 0 goes under 1, that's photon blockade, or above 1, which is photon-induced tunneling. And click again. Okay, so this just indicates these regimes, yeah. But of course, G2 measurement is not sufficient to exactly infer the information about all of these different photon states that we generate at the output. And for this reason, we recently studied measurements of higher order photon correlations on the same system. So it's basically the same type of measurement, but instead of doing measurement of the second order correlations, we measured third order and fourth order correlations. So third order correlations are really correlations between 3 photon events. Tau 1 would be time between first and second photon, and tau 2 between second and third photon. And click. Click. And this is an example of the measured third order correlation function for the laser beam that's exactly at the empty cavity frequency. Horizontal axis plot on the right, two-dimensional plot gives G3 of tau measurement. Tau 1 and tau 2 are these delays between first and second and third photon. And the reason why we see dots and not continuous measurement is because we do probing with a pulsed laser, so separation in 13 nanoseconds. And one thing that you can notice right away is all of these peaks have different amplitudes. They are not constant amplitude as they would be for a Poissonian source. So clearly, the statistics at the output is not Poissonian. So click again. We can also perform the same measurement as we did for second-order correlation function. This is a time delay 0, so only central peak. But here we measure it as a function of the detuning of the input laser from the empty cavity frequency on the horizontal axis. So the blue curve, this bell-like curve, is basically the same as the curve I showed you before that shows transition between photon blockade and photon-induced tunneling. And the green curve is the same type of the curve, but for the third order for photon correlations. And again, both of these deviate from 1, which means that the statistics is not Poissonian. In the inset of this plot, you see what happens with both G2 and G3 as we increase the probe laser power, basically increase the intercavity photon number. And in this case, we saturate the system, and as expected, we should see both of these converge towards 1, because after we saturate the system, we just transmit laser through an empty cavity, which means Poissonian statistics at the output. And this saturation behavior also indicates that observing this sub-Poissonian and super-Poissonian behavior originates in the cavity QED effects. Okay, click. And this is just an example of how far we managed to go. We have also measured fourth-order photon correlations. So now you see this three-dimensional plot. Tau 1, Tau 2, and Tau 3 axes correspond to delays between first and second, second and third and fourth photon. And all the dots in this plot correspond to correlations between these different 4 photons. Again, you see the dots don't have the same color or amplitude. The central dot at 0, 0, 0 is G4 of 0, so that's kind of like for coincident clicks of all of these 4 detectors. And the fact that all the dots have different colors indicates also that the transmitted statistics is not Poissonian. And click. And you can also track G2, G3, and G4 higher order statistics. This is in this case for the central peak. From this measurement, we can infer that for this particular laser frequency and condition, we have primarily generated higher order Fock states. Okay, click. All right, so from the previous experiments, it's clear that we can use transmission through the strongly coupled system to generate non-classical light. But it's also clear that we don't generate pure non-classical states, Fock states. In each of these conditions, we generate some combination of the Fock states, which is different from Poissonian statistics. So we don't generate, for example, exactly 2 photon state. We still have some presence of 1 photon state, vacuum, and 3 photon state. So the question is how we can improve this. And the trivial approach would certainly be to generate more strongly coupled cavity QED system where all of these eigenstates would be more separated, cavity Q factor would be higher, so line widths and broadening of these eigenstates would be smaller. And in that case, once we excite, for instance, first manifold, we would not be able to excite the second manifold. But this requires overcoming some serious fabrication challenges and also leads only to limited improvements. And the reason why it leads to limited improvement is because in terms of the coupling strength G, we're already at 70% of the maximum, so we can't do much better in photonic crystal cavity. And also in terms of the Q factor, maybe we can increase it by a factor of 3 or so, and then we reach the absorption limit of the material. So instead of doing this, we decided to start a couple of different approaches. Click. In this case, we can generate higher quality non-classical light without really requiring to improve cavity Q factor or the coupling strength. And the 2 approaches that we're studying at the moment rely on using a single cavity with multi-level emitter. So not really 2-level emitter as we had in the past, but instead 4-level emitter as outlined here. And click. And the other approach is using a 2-level emitter, but then instead of using a single cavity, using multimodal cavity or photonic molecules. And this is based on proposals initially by Savona and others that we extended to quantum dot photonic crystal cavity systems. So let me start by telling you a little bit about this strongly coupled system of a quantum dot and photonic molecule, and then I'll tell you about multi-level emitter. Click. So now instead of using a single cavity, we use molecule. Click. In this case, we have 2 cavities that are mutually coupled.
Click. And as expected, we should see bonding and anti-bonding states, supermodes of the system. And the separation between supermodes should increase as we increase the coupling between resonators. And in photonic crystals, we increase the coupling by reducing the distance between resonators. As you see here, as we reduce the number of holes between resonators, coupling increases and separation between supermodes increases. And we can also control the direction in which we couple these resonators. So you see them either horizontally or diagonally coupled. For these particular resonators and the fundamental modes, coupling along the diagonal is higher. So we use that technique for performing experiments that I'll show you on the next slide. Click. Okay, so now we have the system of two coupled resonators and quantum dot inside of this photonic molecule. And we demonstrate that we can achieve strong coupling regime between these three oscillators, quantum dot and the two supermodes. And as a signature of that, you see experimental results on the left, where you see anti-crossing of the quantum dot with both supermodes in the spectrum. So on the right hand, you see anti-crossing in B with the lower supermode, and on the A, you see anti-crossing with a higher supermode. So we tune it across both peaks and see anti-crossing. Click. Theory predicts this only if you have the system of three strongly coupled oscillators. So that's on the left side of the theoretical plot. On the right side of the theoretical plot, you see what would happen if you have quantum dots inside the one cavity and strongly coupled to one mode only, and the situation where the two large cavity peaks just correspond to two modes that are not mutually coupled. Then anti-crossing happens with only one peak. Okay, so now we have a system, strongly coupled photonic molecule and a quantum dot. The question is, what can we use this for? And the idea is to use it for non-classical light generation. So click. Based on these proposals by Savona and others, it turns out that if you shine a coherent state onto this system, in transmission you should see sub-Poissonian light, and it should be better anti-bunched for the same coupling strength and cavity field decay than for just a single cavity and quantum dot. Click. And theoretically, for the system with our current parameters, we expect to see G20 approaching 0. So this is theoretical plot. We haven't done experiments yet because this requires some challenging experimental setup in which you excite only one cavity spatially. But considering that the separation between the two of them is just a few microns, that's pretty challenging to do in the experiment. So click. Yeah, click one more time. Yeah, so as an alternative to this, we can also use bimodal cavity instead of photonic molecule, where we have a single cavity with two doubly degenerate modes, quantum dot equally coupled to both modes. It's a very similar configuration. It's a little bit simpler to perform experiment on because we can select the two modes based on the polarization. And again, we expect to see strong anti-bunching as shown at the bottom. We're working on that at the moment. Click. Photonic molecules as a platform are also interesting to extend into these cavity arrays. Here you see experimental study of coupling in the cavity arrays consisting of 4, 9, and 16 resonators. In this case, we have shown that experimental coupling strength in these arrays is greater than the disorder. Click. And if you imagine that you have a single quantum dot in each cavity inside of the array, then such a platform can be used for quantum simulation, as has been theoretically described in these references. We are not there yet. We basically have photonic molecule with a cavity inside, or these arrays with a lot of quantum dots inside, but not single emitter per cavity. But this is certainly something that we're working on, is because it could be used as an equivalent platform to optical lattices for quantum simulation experiments. Click. As in another approach towards generating non-classical light with higher purity, we're also looking into these 4-level emitters in cavity. Click. So this is still 2-level emitter, but if we go to proceed to a 4-level emitter in the cavity, it turns out that for the same G and kappa, same cavity parameters as shown on the bottom left, if with 4-level emitter, we can get much better anti-bunching than for a 2-level emitter. And the reason why that's the case is shown on the right, where the left two plots correspond to practically first and second manifold for the 2-level emitters strongly coupled to the cavity, And the right two plots correspond to first and second manifold of a 4-level emitter coupled to a cavity. And you see that you have 3 eigenstates in the first manifold, 4 eigenstates in the fourth manifold, and their spacing and arrangement is such that you can more easily separate the eigenstates than in the case of the 2-level emitter. So the idea here is to pump the central state in the first manifold and filter out single photons. So now the question is how to implement a multi-level emitter using quantum dots. This is something routinely available in the atomic physics systems, but in the past we mostly worked with the 2-level emitters. Click. And to achieve this, we can use quantum dot, which is charged with an extra electron in this particular case, with magnetic field applied perpendicular to the quantum dot growth axis. We end up with a 4-level system with optically active transitions. 2 bottom states are spin up and spin down electron states, and the top 2 states are trion states, electron hole pair and an extra electron. And on the left, you see experimental result measurement of the photoluminescence from such quantum dot after magnetic field is applied to split these transitions. The 2 inner transitions are vertically polarized and the outer transitions are horizontally polarized. Click. But we need the 4-level emitter inside of the photonic crystal cavity. And to do that, we also want to deterministically charge quantum dot with an extra electron, not like in the previous slide where it was just probabilistically charged by tunneling a carrier from a neighboring heavily doped layer. We have recently managed to do that in this configuration where we have a PIN junction embedded inside of the photonic crystal membrane. When we bias the structure with appropriate bias, then we can preferentially tunnel 1 electron into the quantum dot, and that's also shown in the tunneling plot. And we have a photonic crystal cavity surrounding everything. And then on the right, you see 2 plots showing photoluminescence from the structure. Broad line is the cavity line, and narrow lines are quantum dot lines. The left plot is without magnetic field, and the right plot is the same structure with magnetic field. And what is interesting is you see that as you increase the bias on the horizontal axis, some of these transitions disappear and new transitions appear, right? So some of them break and the new ones appear. And the new ones correspond to charge states of the quantum dots, which split at a higher magnetic field. So we clearly have controllable charging. If we bias this structure to 1.5 volts or so, we would be in the charge states for the quantum dot. Click. And again, showing that these transitions are indeed charged and exhibit this 4-level structure as shown on the left. Click again, a few times. We expect to see these horizontally and vertically polarized transitions, which split as a function of magnetic field. And indeed, we do see that. So these are spectrally resolved peaks on top right. And click one more time. And we do see Zeeman splitting. These transitions separate as a function of the applied magnetic fields. So we do indeed have a 4-level system structure in the cavity. Click. In addition to the non-classical light generation, this 4-level system structure is very interesting for implementing spin-photon interfaces for quantum repeaters. Namely, electron spins in the quantum dot have much longer coherence times than excitons that we worked with in the past. And several other groups have done experiments, really pioneering experiments over the years on this particular platform. I believe you heard from Duncan yesterday. His group has been leading the effort in that direction for many years. The idea here, again, you probably heard about it in Duncan Steele's talk yesterday, is to perform spin initialization and spin manipulation using these quantum dots in the cavity. And we can pick one of the lambda systems inside of this 4-level structure shown on the top right, then use the laser to pump one of the transitions, and then use another pulse laser to perform spin rotation between the up and down state. So with the laser tuned to the V transition, in this case, we are pumping spin into the spin up state. And bottom left shows the experiment where we indeed perform spin initialization. So bottom left, as we tune the broad line on the left, the colorful plot first on the left. As we tune the laser, these side transitions light up, which means that we're pumping spin to spin up or spin down state. And the rotation pulses are tuned to pi pulses and are on all the time. And on the bottom right, you see spin initialization time, which we can measure from this experiment, which is on the order of 5 nanoseconds. So it takes us about 5 nanoseconds to use this optical method to pump electron spin into spin up or spin down state. Click. However, if we embed this 4-level system in an appropriately chosen cavity, it turns out that we can reduce the spin initialization time by quite a lot. So click a few times. An example of that is shown here in the theoretical fork. If we use this bimodal cavity with 2 doubly degenerate modes shown on top right, and if we place a laser again on the same transition, let's say V transition, and the cavity on the H transition in the lambda system, it turns out that we can reduce the spin initialization time to about 300 picoseconds. Click. One more time, yeah? So in this case, we have fidelity, which is nearly 100%, but spin initialization time is on the order of 300 picoseconds, so more than 10 times shorter than in the experiments we performed so far. And this is something that we're working on at the moment because we can achieve huge speed up relative to the configuration we used before. Click. Not only that, we can also use this ultra-fast laser or combination of lasers to manipulate electron spin once we initialize it in one of the states. Here you see Ramsey fringes for the same system. We can basically use 2 pi-half pulses or longer pulses to rotate the spin once it's initialized everywhere on the Bloch sphere. So this would be a movie, but I don't think the movie works because I didn't send it with the slide. Just shows that we can rotate the spin everywhere. Okay. So now, next slide, I'd like to spend the last couple of minutes telling you a little bit about some of the other advancements we have made and the other platforms that we can use. Click again. So far, I talked about photonic crystal cavity and quantum dot, where we can achieve coupling strengths G of up to 40 gigahertz, theoretically. And this is a big improvement relative to atomic cavity QED platform. But it turns out that we're limited to coupling strengths around 40 gigahertz with the mode volume of photonic crystal cavity. What we're looking on at the moment is shown on the right. We are looking into deep subwavelength cavities where we can achieve coupling strengths even greater than 40 gigahertz as a result of the very small optical mode volumes of these structures. Click. And as the first step towards that, we have made this nanometallic cavity with a single quantum dot. Vlad Shalaev probably spoke about their plasmonics and nanometallics effort yesterday, so this is related to that, but involves single indium arsenide quantum dot in gallium arsenide. So now click again. We etch a tiny pillar here in gallium arsenide surrounding quantum dot, and then click again. Using fabrication method, coat only walls of this pillar with silver. So, and that way we obtain a tiny subwavelength cavity. Click again. So here's how the fabricated structures look like on the top. This is just the pillar, and on the top right is after the silver deposition, and pillar has diameter of around 100 nanometers and contains a single quantum dot inside. Optical mode volume is very small. Bottom pictures show optical field in this structure. Optical mode volume is around 20 to 25 times smaller than in photonic crystals, but quality factor is also very small, and that's because of the absorption losses in silver primarily. Click. We have shown a strong Purcell enhancement in this structure. So what you see here is the time-resolved measurement for excitonic lines inside of this cavity, where Purcell enhancement, spontaneous emission rate enhancement of the factor of 8 is extracted. And we know from theory that coupling strengths, in this case, can be on the order of 140 gigahertz or so. We have also measured polarization of the output photons. This particular structure has 2 doubly degenerate modes, and these are polarization measurements at the output for both of these modes. We see that 5 to 10 times light is collected more than in relative to the bulk material using a lens with numerical aperture of 0.75. So we have both strong Purcelling effect of around 8, plus this antenna effect, better collection efficiency on the order of 5 to 10. Click. Click a few times. And again, okay, so to prove that we are really probing a single quantum dot here, again, the same indium arsenide, gallium arsenide quantum dot, we measure second-order photon correlation function for both polarization, excitonic polarizations. We see very strong anti-bunching, proof that it's indeed a single quantum dot. Click again. And we collect, that's okay, click one more time. And we collect around 155,000 counts, single photon counts for 80 megahertz excitation. These are actual measurements on each photon counter in the Hambury, Brown, and Twist type setup. So this is pretty good and on the order of really good distributed Bragg reflector cavities. And it's around 50 times better than for quantum dot in the bulk, which is expected. It's a combination of per cell factor of 8 plus extraction efficiency, which is better by a factor of 5 to 10. Click again. So what is this cavity useful for? Well, we already have a bimodal cavity with pretty good quantum dot cavity coupling. It has 2 doubly degenerate modes. It has strong per cell enhancement. Click. Click again. So this could be useful for a variety of non-classical light generation proposals. On the bottom left, you see references to the paper that I already mentioned with the bimodal cavity. You can also generate entangled photon pairs more efficiently because you have broad enhancement from such a structure, which enhances both biexcitonic and single exciton transitions. And on the bottom right, you see something that we're working on at the moment. Again, we have doubly degenerate cavity that enhances both H and V transitions in this system, and that's exactly what we need to perform more efficient spin initialization and manipulation. And we have already shown that we can observe singly charged quantum dots in such structures. So the bottom right picture shows these outer horizontally polarized and inner vertically polarized transitions for a single charged quantum dot inside such cavity. Click. Oh, click a few times. So in summary, quantum dots in photonic crystal cavities or optical nanocavities are interesting as a platform for quantum optics, cavity QED, nonlinear optics, but they're also useful for applications ranging from quantum repeaters and quantum simulators or quantum repeaters, all the way to potentially building optical interconnects, optical switches, modulators. I mentioned that all optical switch with single photons, the experiment that we did with the cavity QED system. And they also have potential applications in biophotonics that I didn't get a chance to talk about today, but you can imagine putting these devices into cells and tracking what goes on in the cells. And I know some of the related work has been done also at Harvard. Misha probably spoke about it yesterday. Click. Just to acknowledge our funding from Air Force and ONR, and the people who contributed to the work. This is from my current group, my graduate students, Armand Rundqvist, Clem Fisher, Yusuf Kelaita, and postdocs Konstantinos Lagoudakis, Tom Babinek, Kai Muller, and Tomas Sarmiento. And click one more time. And from the previous groups, because I showed some of the older results, my former graduate students, Dirk Englund, who is now at MIT, Andrei Faraon, who is at Caltech, Ilya Fushman, who is at Dropbox, Arka Majumdar, who is transitioning from Intel to University of Washington, and my former postdocs, Michal Bajcik, who is now at Waterloo, Eric Kim, who is at Hitachi AGST, and my former visitor, Pierre Carr, who is at Denmark Technical University. And thank you very much for your attention.